Hi, I'm Nafil Nipu. I'm a PhD student at Electronic Visualization Laboratory at University of Illinois Chicago. Today I'm going to present our work which was done in collaboration with computational fluid dynamics experts. An aircraft is flying over us, leaving behind white line-shaped cloud-like trails. Have you ever wondered what these trails are? Why and how do they form? Why are they sometimes present and other times not? These trails are known as contrails. Essentially, aircraft engines emit hot gases and particles such as soot. When the ambient temperature is low and there is high humidity, these soot particles can condense the surrounding water vapor into ice and they become visible. Under the right conditions, contrails can persist and spread up to several square kilometers. Like regular clouds, they provide shade but also trap heat radiating from Earth's surface, causing warming of the air below, and so they make global warming worse. In fact, contrails account for more than half of the entire climate impact of aviation. Computational fluid dynamics experts, like our collaborators, analyze contrail formation using aircraft engine simulation models. These models are complex and require high performance computing power. They also take different input parameters and boundary conditions. The output of these models are spatiotemporal multivariate data, often in the form of ensembles. Contrail modeling stands to benefit from visual analysis. Visualization can help define contrail characteristics in a meaningful way, such as capturing the contrail shape, can identify relationships among the input, output, and the engine or fuel model used, and expose modeling errors. It could also support the comparative analysis of ensemble members. However, visual analysis needs to meet several challenges. First, contrail characteristics are not well defined, hence identifying the contrail structure, the contrail shape, and characterizing its evolution in meaningful visual ways is difficult. Complex computational modeling tends to introduce modeling errors, which need to be exposed. Contrail simulations also depend on an unusually large number of parameters, and visualizing these many parameters is challenging. Last but not least, the HPC generated data is very large, which poses a challenge to effective visualization. Our contributions are a characterization of application domain of the contrast properties and formation criterion, algorithms to detect contrast structures and their evolution over time, the design and implementation of a novel visual analysis system, and the evaluation of this system with two domain experts. There is a large body of related work described in the paper. However, we handle a new problem with different challenges, including softly defined features, large data, many parameters, and detailed ensemble members. Our overall system consists of a complex computational backend and a visual frontend. Due to time constraints, today I will only talk about the contrail formation, the contrail shape analysis, and a few aspects of the visual frontend. But first, a few words about the project data. The HPC data is large and includes the categorical input and model parameters. The simulation result is ensemble members, also referred to as simulation runs. We had 29 simulation runs, 10 containing the fully grown contrail structures. Our work started by considering a criterion for contrail formation and a derivation of the saturation curves for liquid water and ice. When a fluid element traverses through the mixing line, it first reaches ice saturation, then liquid saturation. If the mixing line does not cross the liquid saturation curve, the contrail will not form. We use this criterion to identify soot particles that will be encased in ice. Next, we develop simultaneously the contrail characterization and the visual frontend. The final design consists of four views. The IO parameter view described in detail in the paper, a 3D plume projection view showing the axially symmetric exhaust and a contrail evolution view, and the similar shape exploration view on which I will focus for this presentation. This panel supports defining contrails characteristics and identifying similar ensemble members based on shape characteristics or IO parameters. It is supported by the backend as follows. For a specific time step of a simulation run, we consider the xy coordinates of the ice particles projected to 2D. For that time step, we then calculate the alpha shape using Adels-Brunner's algorithm. The alpha shape captures the boundary of the points. Last, we chronologically collect the alpha points to capture the shape of the contrail. We then extract the shape characteristics such as area, length, height, and slope. Finally, we apply KNN with Goward distance to each member pair to determine the five most similar members. We evaluated our solution through repeated feedback sessions and two case studies involving two domain experts who are also co-authors of this paper. The case studies were conducted remotely during the corona pandemic using screen sharing and note taking along with the think aloud method. We describe here in abbreviated form one of the case studies which focused on exploring contrail shapes and validating the similarity approach. To achieve these goals, the experts used the system to examine 10 simulation runs that contained the final full-grown contrail structure. They noticed the simulated contrails started to form correctly at a distance from the engine exit. Using the shape view, they then noticed two groups, one generating narrow contrail shapes and the other wider shapes. Analyzing further the wider shape group, they noticed small contrail structures near the jet exit and larger contrail structures with multiple spikes further away, consistent with the underlying simulation model. After discussion, they conducted that the spikes were due to ice particles that traveled further from the main group during the simulation. The wide-shaped members tended to have lower mean temperatures than the narrow-shaped. Surprisingly, some of the narrow-shaped members, even though they had lower areas, contained large number of particles. The proposed visual analysis system yielded excellent feedback from the domain experts. They noted that the shape view could help them to identify suitable parameters for contrail formation. They further appreciated the ability to explore and validate contrail structures, including across multiple runs, which they could not do before. They further commented on the performance and applicability of this work to engine simulation research. Contrail simulations are used for environmental predictions, and so it is necessary to assess modeling errors and behaviors. Our blended computation human approach was successful. Our system allows validation of models and simulations and identification of unusual attribute values and anomalies. Our system further supports identifying and analyzing contrail characteristics, the temporal analysis of contrail structures, and the analysis of similar simulation runs. In terms of design lessons, through an ACD approach and visual scaffolding, we introduced customized novel encodings to our domain experts despite low initial visual literacy. For example, a novel tile glyph to show input parameters and boundary conditions, and a custom tracking graph. It was important also to provide both overviews and details for data exploration, and it was important to link the inputs and outputs. In terms of scalability, the tile glyph scales well with the number of parameters, filament plots scale well with time points, and filtering can help with the number of runs shown. The 3D plume projection view allows comparing only two time steps or models, but the shape analysis view supports multiple simulation runs. The tracking graph works well for a limited number of nodes and links. In terms of generalizability, our system could be generalized to other CFD problems such as fluid mixing. Our custom encodings could be used in the analysis of spatiotemporal data or ensemble simulation data. In conclusion, we presented a visual computing approach to support the analysis of contrails, including methods to detect and analyze contrail structures and their characteristics, and a visual frontend featuring custom encodings. The evaluation of the resulting system shows the success of our approach in contrail investigation. Thanks are due to the Electronic Visualization Laboratory, our collaborators, and the funding agencies. Thank you.